Alright guys, welcome back to Underground Science, and let's talk about Demurcuration. And this is, of course, hydration. This is the part 2 video. So first off, let's start off by remembering what we know about acid-catalyzed hydration. Okay, so we're not going to go over the mechanism step by step because we should know it since we went over it in the past couple of videos, right? And so what happens here is eventually when this nucleophile attacks, right, our hydronium to pick up a hydrogen, eventually we get a carbocation intermediate, right? Because this is acid catalyzed hydration, so we do get carbocation intermediates as compared to oxymerc, we don't get carbocation intermediates. But we're talking about acid catalyzed hydration, right? So once we see this carbocation intermediate, remember we said watch out for the next door carbon, right? And in this case we get a carbocation rearrangement, meaning the hydrogen, right? So let's change colors. The hydrogen that was here will actually shift down. That's why it's called a hydride shift. And once it shifts down to this carbon just lost an electron, right? Because it was bound to hydrogen, but it lost this electron because the hydrogen was shifted to this carbon. So now we have a positive charge here. And if we compare these two carbocations, this is a secondary, this is a tertiary. Tertiary is more stable, so that's why this hydride shift occurs. And eventually we get the OH on this tertiary carbocation, right? Eventually, so that eventually the product would be something like this, right? And that's acid catalyzed hydration. So it's good to keep this in mind that here we do see carbocation rearrangements because it's acid catalyzed hydration. But when we go over the mechanism for, right, in this example, for oxymerc, even if you have this similar compound here, right? Even if you have this compound here in which there's a possibility of a hydride shift, but the reagents are for oxymerc and demerc, there is no hydride shift because a hydride shift only happens if there's a carbocation intermediate. And there's no carbocation intermediate in oxymerc. So if we look at an example problem here, right, in the previous video we mentioned how this mercury bound to the two acetates split up, and the main thing we have to focus on is this mercury acetate, right, compound, and this becomes the electrophile since it's electron poor, and this is electron rich, so it's a nucleophile. This double bond area, right, this alkene will act as a nucleophile and attack the mercury, which will lead to something like this. And when it leads to something like this, right, so this is the new bond that we just formed, but I'm drawing the positive charge here just to make it easy to depict that next what happens is this mercury with this lone pair attacks this electron poor carbon. But in reality, there is no carbocation intermediate because this is very short-lived. Okay, this carbocation is very, very short-lived. So it's said that oxymerc basically does not have a carbocation intermediate. And so once this mercury attacks, we have this mercurinium, right, intermediate, which we also went over in the previous video. And one thing to know here, you may be thinking, okay, this is the same example as previous video, but the reason is, notice so because we didn't have a carbocation intermediate, right, we did not have a hydride shift, okay, that did not happen because there is no carbocation intermediate. So that's what I was trying to show by showing this similar example, and not to mess it up with acid catalyzed hydration where we actually would draw this hydride shift and the carbocation would no longer be here, it would be on this carbon if it was acid catalyzed hydration, but it's not. So now that we know it's not, right, everything will proceed the same way. We have the mercurinium intermediate, and again, you note down immediately that, okay, these two carbons were involved in the double bond, right? This carbon's primary, this carbon's secondary, so the water, right, that will come next will actually attack the secondary carbon, which will lead to something like this. Let's go switch back to orange. So once the water attacks, we're going to have this next intermediate where this bond will break again, and this is going to be bound. This is going to be bound to the oxygen. That's part of the water molecule, and we're going to have a positive charge here. All right, and let's take this to the next page to see what happens next. All right, so here we are, right? This is where we're at right now. And again, because we have plenty of water in this solvent, right? Because that's part of our solvent. Water, the oxygen in water, right, can come and take this hydrogen away to make an OH, or an acetate ion can come in here and take an H and make this an OH. Either one. Okay, so let's say the acetate ion did that. Then that means this acetate ion would gain a hydrogen, which would turn into acetic acid, which looks something like this. All right, and then this compound would turn into, the only thing that would actually be left, right, would be this mercury bound to the acetate. And then let's draw this C in a different color so we can tell. And then this carbon, right, remember we just drew this, the hydrogen going away, so now we have an OH, that's it, here. And then to get rid of this, remember we do demurcuration by adding sodium borohydride, and this was the second step in oxymerc demurc. And then we end up basically taking the help of these hydrides and reducing this carbon so that the product ends up being something like this. And then we'll draw the hydrogen in right here instead of the mercury bound to the acetate, and then here's the OH. So see, it's still hydration because the double bond used to be here, and we added a water across the double bond because OH plus H equals water, right? And so this is our product. And notice that the OH was added to the secondary carbon. This is secondary, while the hydrogen was added to the primary carbon. So from this we know that this is also, right, oxymerc demurc is Markovnikov addition. All right, and that's basically it for this video. In the next video, we'll go over more reaction examples and mechanisms. All right, so I hope to see you guys there.